Soil erosion is a complex and multifaceted process that can be defined as a movement of soil material by processes of wind, rain, overland flow, and gravity. Soil erosion is a major issue of agricultural, post-mining, and native systems, and is also a direct indicator of land degradation. Soil erosion can be measured and can indicate the success of rehabilitation or as a process of designing landscapes for rehabilitation. Different soil types vary in the susceptibility to erosion. Factors that contribute to certain soils being susceptible include particle size. The finer the particle, the easier it is to transport and hence move downslope. On the other hand, soils can be cohesive and sticky or non-cohesive, such as sand grains. External energy in the form of raindrops, turbulent eddies from wind and water, or gravitational energy can move a particle of soil. Soil erosion is also heavily influenced by slope of a landscape. Generally, the steeper the slope, the more erosion occurs, as sediment can be suspended in the surface runoff and is able to travel easily downslope. Erosion as a process cannot be avoided and is part of all landscapes, but can be decreased and monitored by environmental modelling. These models can be conceptual, empirical, physical, or mathematical.
Rainfall is one of the most common causes of erosion. Rain may move soil directly as indirectly. The amount of rain, the intensity of rain, and the frequency of rain will have an effect on the rate of soil erosion. Rain impacts erosion directly as splash erosion. This is only effective if the rain falls with sufficient intensity. When the raindrops hit bare soil, their kinetic energy is able to detach and move soil particles a short distance. As soil particles can only be moved a few centimeters by this process, its effects are solely on site. Although considerable quantities of soil may be moved, it is all merely redistributed back over the surface of the soil. According to Kwanzaa 2006, as rainfall intensity increases, particle detachment and transport increases. This is due to the increased kinetic energy associated with increasing intensity. In a study in the same article, it showed there was less detachment in clay and clay loam soils, such as the soils present in our catchment. This indicates that these soils are more stable than the sandy soils, since rain splash is a measure of the stability or resistance of the soil to raindrop impact forces. Rainfall may also move soil indirectly by the means of runoff in rills or gullies. Rills are small gullies which can be removed through management techniques such as tillage, while this is not possible for gullies as they are too big. Gully erosion is commonly triggered or accelerated by land use change or extreme climatic events, which with climate change are becoming more common. The greater the intensity and duration of a rain event, the higher the erosion potential. This is because runoff occurs for two reasons. Firstly, if rain intensity is higher than infiltration, runoff is generated. This runoff is known as infiltration excess runoff. This runoff would not occur if the rainfall was less intense, while runoff also occurs if the soil is already fully saturated. Runoff which results from this situation is known as saturation excess runoff. This can be due to both intensity, frequency, and the state of the soil. During periods of frequent, high-intense rainfall, a greater percentage of the rainfall will become runoff. This is due to high soil moisture or saturated conditions, as water cannot infiltrate if the soil is already saturated.
The aim of this experiment is to compare the rate of erosion between soils exposed to different intervals and intensities of rainfall. Furthermore, Major objectives of this experiment include gaining an understanding of the relationship between erosion and rainfall and to improve current knowledge on the interaction of soil properties within the environment. In this experiment, we hypothesized that soil profiles under high rainfall intensities will obtain and maintain a higher rate of erosion and runoff as higher intensity of rainfall is believed to result in activities that disturb the land surface and force rates of transport of sediments and soil to be higher.
Soil collections were taken from a mine site out of Perth by Dr. Gavin McGrath. These consisted of clay loam soils that comprised of large quantities of non-porous rocks. The soil was comprised of a mixture of gravel, sand and clay, mixed with the larger limestone rocks. This created soils that had a light beige yellow colour. Initially, we set up 3 replicates for each of the 2 experiments. Approximately 30 litres of river sand was filled into the non-porous metal tub, which was then filled to capacity with the given soil. Soils were compacted with shovels and wooden blocks to promote runoff and erosion instead of infiltration within the soil. These tubs had a surface area of approximately 0.55 metres squared. A device to collect runoff was attached to indicate the change in rainfall intensity on soil erosion. The soil profiles were placed on a 10-degree slope to encourage excess overland runoff down the soil profile. To simulate rainfall flexibly and efficiently along the study period, which was just under an hour, we used similar methods to Locke 2000 and Locke et al. 2001. This involved using a flat fan V-Jet 80100 nozzles mounted on an oscillating manifold. The nozzles were controlled to represent sweeping rainfall on the soil profile across a 2.5 metre wide area. Although the rainfall intensity was kept constant, the rainfall frequency was controlled by determining the time nozzles would rest after completing a single rainfall sequence across the soil profile. The rainfall frequency was altered to pause for intervals of either 10 or 3 seconds after a rainfall event had occurred between each experiment. Soil runoff was collected by catching the runoff from the soil profile with pre-weighed beakers. Runoff was measured for 30 seconds and 3-minute intervals to gain a representative analysis of how runoff and erosion varies across the experiment. The beakers used to measure runoff, and hence erosion, were put in the oven to dry to measure the flux in sediments from the soil profile. To calculate rainfall intensity, sediment flux, and infiltration, we use formulas related to the level of rainfall, runoff, and size of the catchment. A 2-way ANOVA test was used to eliminate rainfall as potentially responsible for the difference between replicates. Finally, a correlation test was performed to assume confidence that the sediment flux was as a result from the different rates of runoff.
The times to runoff were assessed to identify whether conditions amongst the 3 replicates were different from one another. Tray C displayed significantly faster times to runoff than the other replicates in both rainfall intensity simulations. In the first experiment, this was by a rate of 49 seconds, and in the second experiment by 15 seconds. Therefore, Tray A and Tray B also showed similar rates to runoff in both experiments. This indicates that Tray C as a replicate was dissimilar to the other 2 trays and therefore has slightly different characteristics that need to be considered before determining mean erosion rates of the 3 replicates. To assess whether the observed differences in runoff times among the 3 trays were influenced by surface roughness and an ANOVA test was performed to eliminate different rates of rainfall as a factor. The raw mean values for each tray and at each different rainfall rate is presented. From both the raw data and visual representation, it is clear that no significant difference occurs amongst the three trays, hence indicating that rainfall received at each tray was similar. Here, at each time step, it can be seen that different gauges display the maximum rainfall rate. Results from this analysis therefore confirm the suspicions that differences amongst replicates were as a result of surface roughness with increased compaction and smoothness observed in tray C. Comparing differing infiltration rates indicates major differences amongst the two experiments. The time to negative infiltration highlights the time to saturated conditions. In the first experiment with decreased rainfall rate, negative infiltration occurred at 30 minutes. As a result of the increased rainfall rate, saturated conditions were obtained within 5 minutes. Although a faster time to saturation is expected and confirmed by literature, these results are influenced significantly due to the second experiment occurring on already saturated soil. Therefore, this acts as a major limitation in comparing erosion rates with differing rainfall intensities and decreases the accuracy and credibility of our results. To be confident that changes in sediment flux rates are as a result of differing runoff rates, a correlation test was performed which yielded a correlation coefficient of 0.84. Hence, sediment flux exhibits a strong positive relationship with runoff, and therefore we can dismiss other factors as influencing the erosion rate. The effect of different rainfall intensities upon soil erosion was then investigated, which found that an increased rainfall intensity resulted in a far greater sediment flux rate. The rainfall intervals of 10 seconds showed no major trend through time, whereas with the increased rainfall intensity of 3 seconds, a decreasing trend through time was observed. Therefore, our initial hypothesis was confirmed that increasing rainfall intensity resulted in a larger component of soil erosion.
There were a number of limiting factors in this experiment which manipulated the results. For one, the control variable in this experiment was not controlled. Trays A, B, and C were all supposed to have similar conditions, but from observation, trays A and B had more rocks, and the soil compaction in tray C was more dense. The soil composition, clay, sand, and limestone, was also not closely monitored. Another limitation, which affected the ability to compare results between the two labs, was the saturation of soil prior to water application. In the first lab, fresh dry soil was placed into the trays, while in the second lab, fresh soil was not placed in the trays. Instead, the soil was pre-saturated from a similar experiment being run 1 hour before our own. The rainfall rate was also inconsistent for both labs due to faulty equipment. The sprinklers stopped working multiple times during each session. Some of those were during runoff collection, which would result in decreased runoff over this shutdown period. The experiment was supposed to simulate naturally moderate and high rainfall events. However, due to the anthropogenic equipment used, the rainfall was not accurate to natural conditions. The intensity fluctuated due to the rotation of the nozzles, which also influenced the distribution of drop sizes and the velocity at which the water drops hit the trays. The hypothesis that erosion rates would be higher where rainfall intensity was greater was supported by this study, although the amount of errors in the experiment warped the results. Therefore, while our results mimic the overall expected outcome of this experiment, they are not reliable and are not recommended to be used for further study. If we were to run this experiment again, a number of changes would have to be made to ensure more accurate results. For one, dry, clean soil would need to be used for each tray, of relative equal composition. The compaction of soil should also be similar, as should the surface roughness. A more reliable rainfall simulator would need to be used to ensure the rainfall rate was homogeneous over the lab session, and the timing of rainfall collection should be precise. In this experiment, the rainfall collection times were not even for both labs. Some were taken 15 minutes apart, others 9 minutes apart. Therefore, more rainfall samples were taken when they were less at more frequent intervals, and the results would be more accurate for these.